The title of this presentation is Computations with the Poisson bracket for Poisson structure of triangular ice. To begin with a presentation overview, we'll be first reviewing some material briefly from the previous presentation, which also has connections with the third presentation on this series, in which we were talking about general aspects of vertex models and how these vertex models can be studied with a quantum inverse scattering approach. So in this part of the presentation, building upon some details and aspects of the quantum inverse scattering method that we had deliberately kept a little bit vague even from earlier presentations in this series, we'll discuss more details on the three-dimensional quantum inverse scattering type approach. And to add on general descriptions that were provided earlier in this series that we deliberately kept a little vague and arbitrary so that we could come back to them in more detail when we had discussed the Ashkin-Taylor model and some other aspects and differences between two and three-dimensional vertex models. We're now going to provide information to address the following questions for making further connections between the two and three-dimensional approaches and discussing a couple of additional aspects in which the dimensionality of the state space impacts how we can implement some type of quantum inverse scattering type approach. And this type of argument is related to the fact that we need to think about how many terms appear from entries of the transfer matrix that we have to approximate from computations with the Poisson bracket. And we talked about how we can define the three-dimensional transfer matrix, and we also had provided in the eighth presentation of the series, the last presentation, how we can define a three-dimensional quantum monodromy matrix in terms of a mapping from a tensor product of two complex spaces. And we were describing all these objects because we are interested in thinking about how do computations with the L operator expressed in the Pauli basis from the two-dimensional setting transfer to L operators in the three-dimensional setting. And as we mentioned in the last bullet point, additionally, we further describe how algebraic connections from the three-dimensional L operator along the lines of those mentioned in the previous part of the series relate to staggering and inhomogeneities in the vertex models. And we're going to allude to some later presentations in this series, which are more closer to the end, in which we're kind of exploring more from these rigorous results and notions that we provide of integrability, how even if you adopt some type of heuristic understanding of different types of systems that appear, whether relating to physics or even biological systems, can be studied with this thermodynamic type approach, and how it's even very good and important to understand a heuristic first before you're trying to make some mathematical argument more rigorous and precise. And so I'm going to be just very briefly overviewing some of the material from the previous presentation in the series. And this presentation of the series was related to the fact that we had introduced some L operators, and we had described how it's given by a three-dimensional representation, and how actually, besides this single instance of an L operator, there's an action of an automorphism, which gives a family of L operators, which yields some broader interpretation with regards to Poisson structure and how one can approximate this system of Poisson brackets that we're going to look at term by term and analyze on a lower level in terms of how individual terms appear in the product representation and how you can make use of these forms to know which family of Poisson brackets you would like to asymptotically approximate in the large infinite volume limit of the transfer matrix. And we had also described how we had defined triangular ice, and it's very much similar to the six vertex model, but the triangular vertex model in three dimensions over the triangular lattice. This vertex model has 20 possible configurations, so it's in correspondence with the 20 vertex model. And then we can see that in the same way that we had talked about in several other presentations, whether it be relating to how one can make use of isotropic parameters for looking at the probability measure of the six vertex height function and establishing that it logarithmically delocalizes under flat and slope boundary conditions. For this case, you can make similar use of these parameters by grouping configurations together, as we see in the leftmost column of this sample space, the two configurations that have all arrows pointing inwards or all arrows point outwards for the 20 vertex model have the same weight. And then by pairing complementary type configurations for the 20 vertex model in the sample space, then we can get, the additional weights that are required to define the weight measure, which is then normalized by the partition function of the 20 vertex model to obtain the probability measure for the 20 vertex model under some boundary condition. And in the last presentation of the series, we had we had begun adding on some additional layers to our understanding of intuition of how these L operators come into play and how they impact the Poisson brackets that we would like to asymptotically approximate. And just to get ourselves started, we were thinking about simple cases from taking products of L operators together and looking at a couple of different simpler aspects as a beginning and as a starting point and as a type of baby step to be able to look at then how additional complexities in these expressions from the product representation would arise. And this is given by the fact that we can look at the span of script B of 1, script B of 2, script B of 3 for a JK, which are the two indices which we had introduced in the reformulation of the three-dimensional L operator. And we can look at spans, the set of linear combinations of all of these types of column representations, and look at how characteristics of the set of all linear combinations of these three representations would then be related to the product representation for the lower orders, and then from which we can extrapolate these observations to higher order terms of the infinite volume expansion of the transfer matrix, and also how it relates to the infinite volume expansion of the quantum monodromy matrix in 3 dimensions. And so we had also reiterated that the infinite volume limit of the transfer matrix is proportional to the infinite volume limit of the quantum monodromy matrix, because the transfer matrix, which is defined as a trace of the product of L operators, it's given by the fact that it's used to define some additional multiplication of a diagonal matrix with this trace of the transfer matrix to obtain the quantum monodromy matrix in 3 dimensions. And this was a particular representation of the transfer matrix that we had looked at, in which we're taking J and K to vary over each one of the directions that we would like to take the infinite volume limit of to infinity over the triangular lattice. And then in comparison to the transfer matrix in 2 dimensions, the transfer matrix in 3 dimensions, it has several different possible representations. And to make parts of the computation simpler so that some terms would drop out when we're looking at various components or entries of the product representation from L operators, or from first 2 L operators, but then scaling that up to 6 and 8 L operators at a time. We have a zero pivot along the last entry of the first column. And when we're talking about vertex models and looking at the transfer matrix and the quantum monodromy matrix, there are various types of ways that we can introduce degenerations or simplifications of some parameters which appear in a vertex model, and then how that can help us still be able to make some conclusions or some observations about the vertex model in a special case, and how then whether we could reimpose some complexity from homogenizing certain parameters or characteristics of the model to determine, how would the result or the conclusion change. And in this case, we're looking at homogenization because we're taking the infinite volume limit to obtain a infinite volume representation of the 3-dimensional transfer matrix and quantum monodromy matrices as M and N go to positive infinity. But also we can think about that associated with each degree of freedom that we're taking the infinite volume limit of for studying some asymptotic characteristics and properties of the higher order terms of the transfer matrix expansion. We can also introduce homogenization of the spectral parameters along each one of the sites, so that the 20 vertex model that we're thinking about and that we're introducing the homogenization for, it can be some type of simplified version in which, more or less, because we're taking an infinite volume limit, the staggering or in the associated inhomogeneities along each side of the lattice, they're set to be the same, which, it's kind of like a nice simplification and assumption which occurs, in some type of more heuristic understanding of, statistical physics and scientific areas that we're going to discuss later in the presentation of the series, and how very much having this intuition in place, it can also help for looking at how different interactions would be sustained either over longer or shorter distances over the triangular lattice for this particular 20 vertex model that we're looking at. And in two dimensions, as we had mentioned, the quantum monodromy matrix is defined by this map, which we introduced, and which is dependent upon a product of diagonal 2x2 matrices and the 2x2 R operator, which is relating to the L operators that we took in two dimensions from the Pauli basis to obtain the transfer matrix. And sorry. And then but in three dimensions, in three dimensions, there's a difference because sorry, excuse me. In three dimensions, there's a difference because because we can have many other parameters which can come into play, and how that can influence the type of computations that we're going to we're going to carry out with the Poisson bracket. So now I'm going to demonstrate how when you adopt if you want to further this intuition of how the structure of the Poisson bracket would be influenced by the higher dimensional state space, in addition to other terms and other terms which appear from the up to Dynkin automorphism three-dimensional L operator. Then we can look at different types of linear combinations of these elements that would represent different interactions that are appearing from differential operators or the mapping into the unital associative algebra, and how we're going to be able to recover and group together different terms from the product representation that are going to enter in the Poisson bracket. And this is the three-dimensional quantum monodromy matrix that we had also defined in the previous presentation of the series. And it's pretty much an extension by one dimension of the previous two-dimensional quantum monodromy matrix, because we have a 3x3 diagonal matrix instead of a 2x2 diagonal matrix, and the R operator, which is relating to the L operator that we've been analyzing and discussing, is dependent upon IA and JB instead of IA, as well as an additional spectral parameter U prime minus V of J prime over each J. And the limit from the previous slide is related to studying the asymptotic properties of the two limits below it, in which we can think about either sending n to positive infinity or L to positive infinity. And then the difference is that we're just taking different indices for manipulating different terms which appear in the representation, in the 3x3 representation of the L operator. And the goal is to be able to incorporate information from both of these infinite degrees of freedom to look at some type of global, larger scale asymptotic infinite volume limit for the L operators, which is relating to the transfer matrix. And so the outcomes in broad strokes that we had talked about from the previous presentation in the series was that we were introducing all objects that were manipulated in the three-dimensional quantum inverse scattering method. And we were discussing how specific terms and lower and higher order approximations of the three-dimensional transfer matrix arise. And we established comparisons with staggering and spectral parameters for the two-dimensional six-vertex model in previous works under domain wall, flat, or slope boundary conditions. And other assumptions that can be imposed on the six-vertex model in this framework relate to either colorizing or looking at the existence of an arbitrary number of colors, which can be accommodated by from the Hamiltonian in the two or three-dimensional Ashkin-Teller models. And so now we're going to be able to further describe how we're building upon these objects that we had defined in the previous presentation of the series, and that we have begun reiterating and redescribing in this part. And so this is related to the fact that as we see in this bottom line here, if we want to study the limit of this product of this representation as m and n go to positive infinity, then this is related to the fact that if we just look at one of the products, we would like to take the number of terms that appear in this product as some type of infinite volume expansion for studying the large scale properties of the transfer matrix. And this is related to the fact that for these different subscripts I, which appear along each one of the components of the representation, we can single out which terms would have the most complicated representation, which would then influence the number of the number of times that we would apply the bilinearity property so that we can obtain a degeneration of a more complicated Poisson bracket into a sequence or a system of Poisson brackets which have one argument in either or one term in each one of the two arguments that appear in the Poisson bracket. And then this would allow us to be able to make use of then at that point observations that we had from the quantum inverse scattering method in 2 dimensions, because we're just going to know that we can, depending upon which block or which group of terms that we have when we're from the two transfer matrices that we're multiplying together, we can then, roughly speaking, approximate that Poisson bracket by the reciprocal of the difference between whatever block that is, which is a function of u, minus whatever block the other portion of the transfer matrix is that's in the Poisson bracket, which is a function of u prime. And so if we want to understand the limit of the form from products of L operators for different J, one really easy step, or one very accessible step to begin with, is just to look at this product representation resulting from these two matrices, from these two L operators. And what that has the effect of doing is measuring different contributions which we have from in the 20 vertex model, when we look at either fixing one I and then looking at this contribution from the contribution of the spectral parameters, the inhomogeneities, or the Q parameters raised to differential operators. And this can allow us to look at different pairwise combinations of interactions from this site, along with any types of interactions for for arbitrary J along the site right next to it. So this is a type of nearest neighbor interaction, because we're looking at the nearest neighbor between one site in one portion of the triangular lattice, in either looking above or below this point. But what this also has the effect of doing is that by varying the J parameter as well, which we're going to get into, and that's how a lot more complicated computations arise, this is going to give us the structure that we can at first kind of eyeball and look at heuristically for what would appear in terms of summations from the Poisson bracket in either one of the arguments. And then that very much gets our foot in the door for approximating the set of this relations of Poisson brackets, just like we had approximated the 16 Poisson brackets for the 2-dimensional and homogeneous 6-vertex model. So beyond expressions are obtained for the product of L operators, such as the span of 3 columns of the 3-dimensional representation below, one must also make use of these relations for higher order terms of the infinite volume expansion of the transfer matrix. So this is to say that even if we look at this product of these two representations for the L operator, we can look at first to demonstrate what is the term of each one of the individual elements that we're taking the set of all linear combinations over. We can look at the first column of the desired matrix of the desired product representation. And this is given by the fact that we're going to have some coefficients in this representation, which are either like q raised to some sum of two differential operators, or we can also have contributions from the Hermitian complex conjugate of a coefficient aji, or even aj2, and so on. And how, once we look at if we look at the middle term in this column of the representation for the product, that we would have then also contributions from a different couple of terms, and we can even see that there's an alternating sign between the Hermitian conjugate of two of these terms, and that there can either exist a C parameter, which is the complex valued mapping into the unital associative algebra, followed by a q raised to some sum of two differential operators, or we can also have a q to the minus 2 term and some other terms which then end with a complex valued unital associative mapping. But besides the first representation, more complicated expressions for several other product representations follow from the fact that this type of representation that we looked at can also be used to obtain some type of information about, as we had mentioned, either the contributions from different Q raised to differential operator parameters when we fix I and J so that we're occupying a certain point within the triangular lattice as we're taking the infinite volume limit. So this is important because then we're almost like fixing the part of the lattice that we're taking the infinite volume limit over, and we're assigning, some type of inhomogeneity or staggering to the site, and we're fixing this static in time. And then after this, as we're taking the infinite volume limit, this part of the environment of the triangular lattice that we're studying for the 20 vertex model, it's fixed and definite. And we would like to then look at how additional staggering or inhomogeneities in new portions of the finite volume that we're taking the infinite volume limit over would relate to the parts of the environment that we've already studied and we've already reflected in these lower order terms of the transform matrix expansion. And once a suitable product representation is obtained for lower order terms, a more complicated expansion with higher order terms is obtained that agrees with all terms of the lower order expansion. So this is just to say that once we do some of those computations for the lower order terms, where it's helpful for us and it's prerogative it's our prerogative to be able to do those computations because those lower order terms they're going to come into play in terms of how the higher order terms are going to just be like additional terms in a summation from groups that we're trying to pair together from the expansion of individual entries of the product representation. And just to spend a little bit of time on this slide, we can see that from all these arrows that I pointed out, we can see several different types of contributions that are appearing from just the representation itself of the L operator before we're taking products of L operators to take the trace to study the transfer matrix, that we can look at how different elements and contributions would appear in the product representation. And this is important because it's going to demonstrate how we can have, as we had also alluded to and mentioned, different combinatorial pairs of interactions for either Q raised to the differential operators, as we see here in the last entry in the second column of the first representation, that we have a sigma or C of Sj of I term, which is some complex valued parameter, complex valued unitome associative mapping. And in the second representation, which appears that we're including to obtain so that we can study the resulting product representation, um, we have we have again just this Q raised to some difference of two differential parameters or differential operators, but it's just that we shift the index of the I parameter, which is given as the index um, to 2 and 3 instead of 1 and 2, and then the superscript of the differential operator that we're raising in this Q parameter is kept the same. So this is again, as we had mentioned, just fixing two nearest neighbors along some degree of freedom of the triangular lattice that we're taking the infinite volume limit of, and then looking at all possible J. And to obtain a more generalized formula for entries of the three-dimensional product representation for multiplying an arbitrary number of L operators together, several other computations follow from observing patterns of how terms from the three-dimensional representation are grouped together. One of the most simple of which is the following. So we can look at much more complicated terms which appear appear in the product representation for individual entries of the product of the L operators. And in this case, we can see that I deliberately chose a different portion of the representation to highlight some different types of patterns and differences which can arise from looking at the product of L operators, like we had mentioned, and how that's going to reflect in more detail how that impacts the Poisson structure and the approximations that we're going to have to that one can make use of from the properties of the Poisson bracket. And this is given by the fact that there are other types of terms, such as given in the first term in the superposition, in which we have some Hermitian complex conjugate of a sub j plus O1 and k plus 1. But then later on, after a couple of terms in this superposition, we also have another term in which we knock down the increment of the k subscript, which appears in the a coefficient by 1, and we're increasing we're increasing by 1 position to j plus 2 instead of to j plus 1. So this is very much looking at how we can either look at j plus 1 or k plus 1, or we can look at a larger portion of finite volume from the from in the associated contribution from this complex conjugate of the a coefficient to either j plus 2 and k. So it's like we're increasing the position in one direction by 1 and decreasing the position by 1 in the other direction of freedom. And from the second term that's given in the superposition, we also have another term which is beginning with the same coefficient, and it's also followed by the same complex or Hermitian complex conjugate of the other a of j plus 2k coefficient, but there are some different terms which appear in the q raised to the differential parameter, the differential operator, sorry, because we're looking at subtracting two differential operators by increasing the index of the subscript of the differential operator by 1 from k to k plus 1. And we can look at several other different patterns which appear from these terms in the product representation, and how pretty much they all amount to looking at different complex conjugates of a terms, or the dagger terms of the coefficients a, in how either different combinations of terms that appear in the product representation can either be comprised of q raised to some differential power, or differential operator, as well as some complex value mapping contribution from c. And then we can also have q to the minus 2 parameters which appear. And as a starting point, we can discuss how components from a few terms of the expression from the previous slide arise, namely these two terms, because they're having, as we had mentioned, the similarity between the two representations that we have at aj plus 1 and k plus 1 that's raised to some complex conjugate. And there's also a contribution in both of these terms of the product representation that there's an a of j plus 2 of k term and appearing in both of them. The only difference, though, is that, as we're going to mention, is that this q to the minus 2 term, which appears in one of the terms, is different in the representation below it in comparison to the representation above, because the representation above has less contributions from these remaining components from the q parameters and the c parameters, as well as the fact that we're having an a of j plus 2k of term instead of an a of j plus 3k term. And so, as we have been alluding to, we can break down the expression from the previous slide in more detail, because we can look at different contributions in which we have this kind of little legend above the representation, the component of the representation that we're looking at, in which we have some Hermitian conjugate of the a coefficients, as well as we indicate in item 2, a q parameter raised to a differential operator, and then finally in item 3, a complex valued unital mapping raised to the s parameter. So we can see that, as we have been alluding to and describing, these similar 1 components appear in the first coefficient and the second coefficient, as well as these 2 components appear in the terms which are immediately preceding the 2a coefficients, as well as finally in 3 we have the complex valued unital mapping terms. But as we can now spell out in further detail, from another term in the superposition that appears from the previous slide, or from 2 slides ago that we were talking about, we can have more contributions in some terms which represent additional summations or additional terms which are going to come into play from the Poisson bracket. And this is given by the fact that, as we had alluded to and described in the previous slide, we're still having the Hermitian conjugate of the a coefficients which appear in these 2 terms here, but we also have these q parameters which appear also later in the superposition, because in comparison to the first earlier term, which was just ending at a of j plus 3 of k, If we have instead a aj plus 2 of k term, then we also have these other terms, which is given by the fact that there's a q parameter that's raised to subtracting two differential operators from one another, as well as a contribution from the unital, from the complex valued unital associative mapping. And then we also have another term, which is representing another type of cross interaction term, which is preceding the d of j plus 3 of k term, followed by a unital associative mapping, which is having a slightly different contribution in the S parameter, because in the previous group of terms, when we were looking at q raised to subtracting these two differential operators from each other, this results in the fact that we also compensate and subtract from this S parameter another Sj plus 2k parameter instead of leaving this S parameter unperturbed in the final portion of the expression that we're getting from this component of the product representation. And so all in all, the expressions from the previous two slides, namely these two groups of terms that we were looking at and just describing some general characteristics and features of that which are representing some simpler, more tame terms that are appearing in the product representation that are influencing the Poisson structure, and how we can talk about, like how we had alluded to in the previous presentation, how one can introduce some type of asymptotic approximation of the 81 Poisson brackets within this system in this family. Share similarities with several other terms from the product representation, including also the second term, in which we pick up some alternating sign of this coefficient, which appears in the first term. And this is very much, expected, because when we're looking at different contributions of terms, we can either look at some type of anti-commutation relation, or looking at, how the contribution would result from subtracting two quantities together, in which maybe we have the same coefficients which represent some type of similar or the same fixed combinatorial aspects of two vertex configurations over the triangular lattice that we want to study, but then we can maybe vary some intermediate parameters to see what would, which would be the higher order term which survives the difference, and how this would also come into play in some type of more complicated superposition of terms. And this is also related to the fact that from the fourth term, there's an even more complicated expression, which includes, as we see here, we still have these two terms, which are the complex conjugate of a of j plus 1 of k and a of j plus 2 of k. But a bit later on in the superposition, we have another cross term, which arises from the fact that we have an aj plus 3 of k term and an aj plus 2 of k term. So we can look at, even like we had just mentioned, looking at more complicated operator, representations of operators, and how this comes from the product representation of the L operators, and how this is going to come into play from the Poisson brackets, which we're going to be describing from these types of terms. But however, as in more complicated expressions for other terms in the product representation, there are other terms that do not begin with a coefficient, such as this type of term, in which it begins with some q raised to some differential operator term. And then it's different because we have some aj plus 2 of k terms, which we're not taking the complex conjugate of. But then we also have other terms which appear later on in the superposition, or in the representation from the product representation of these two complex conjugates of aj plus 3 of k and aj plus 2 of k. So yeah, so I wanted to spend a little bit more time in the presentation of the series breaking down these types of components, and how different patterns and interactions can arise from the L operators, and how we had deliberately left this part, or these aspects of the Poisson structure, a little bit more vague earlier in the presentations in the series, because we were first getting our foot in the door and describing how the three-dimensional objects interact, and how we're looking at how there can be some similarities between the two and three-dimensional approaches, but then there can be many other types of other, complexities and other things that can be tricky to deal with if you're looking at the representation of the product in three dimensions. And ultimately, it is worth reiterating how the structure of the factorization for the universal R matrix in the higher dimensional state space with more structure directly impacts the algebraic and combinatorial terms from the entries of the product representation And like we had mentioned in earlier parts of the series, from page 34 of the reference that we had described from exercises with the universal R matrix, the product representation and the decomposition of the R matrix of the universal R matrix is given by the fact that it has three terms resulting from Q exponential factors, as well as the last term for the K matrix, which, like we had talked about in terms of the lower and higher rank spin chains, is responsible for the encoding of boundary conditions. It can be expressed in terms of an exponential of a tensor product. And it's also worth reiterating that in two dimensions, and as it will be demonstrated for triangular ice in three dimensions, computations with a Poisson bracket for for one group of terms of the transfer matrix are extremely helpful for carrying out computations with the Poisson bracket for other groups of the transfer matrix. So this is just to say that in broad strokes, this type of system and relation and set of terms that we had described in the two-dimensional case, which can be expressed in terms of several different contributions in terms from products of polybases, and looking at even sign of another polybasis element, can come into play because we're going to permute maybe holding some terms or some arguments of the Poisson bracket fixed and being able to permute either terms from the other argument or even varying coefficients or products of coefficients that appear before polybasis elements, and how very much that type of intuition and that type of line of thinking that we have used in three dimensions, it will be a similarity and an advantage that we can immediately use in three dimensions, because we're still going to have to be able to analyze some system of Poisson brackets asymptotically. But the thing is just that we're still going to have two arguments for each one of the terms in the Poisson bracket, but it's just going to be a larger set of relations, like we had mentioned, fit 81 Poisson brackets in comparison to 16 Poisson brackets. And for triangular ice, we still make significant use of bilinearity and Leibniz's rule of the Poisson bracket. So this is just to very briefly show the slide again, because we had already talked about these types of properties, the standard properties of the Poisson bracket, and how we can use different components and different properties of the Poisson bracket when we're asymptotically approximating brackets within the set of 81 relations. And to to further to further demonstrate how having this type of lower order simpler case understanding of the representation for the product of L operators is helpful even for looking at applications of thermodynamics and statistical mechanics in other areas, we can observe that objects for the QISM type approach for triangular ice share in many similarities with reflecting boundary conditions of the six vertex model that are discussed later in the series. This is given by the fact that some more types of algebraic connections can come into play when we're looking at reflecting boundary conditions of the six vertex model, which is related to, as it's demonstrating in this figure that we're going to discuss in the reference later in the presentation in the series, related to the fact that we can assign either some type of spectral parameters along portions of the finite volume, which are either ingoing or outgoing, and how looking at a set of boundary conditions, which is very closely related to the set of domain wall boundary conditions for the six vertex model, provides us with some more type of algebraic connections in two dimensions, because so far in the presentations in the series, we had only really been talking about algebraic connections which appear from the three-dimensional representation, not from the two-dimensional representation. And also in another presentation in this series, we'll discuss how more from a heuristic perspective and how this perspective can be very good and helpful, like how we had first made use of some kind of imprecise observations to understand integrability of triangular ice, how boundary conditions can impact behavior of synthetic biological systems, in which, as part of a workflow that we're going to describe on a more heuristic level, how we can measure RNA degradation from sets of combinatorial targets, and how that very much kind of reflects different contributions that we can have over interactions in some finite volume. Like we had talked about how we want to take and look at fixing parameters, as we're taking the infinite volume limit over the triangular lattice, how that can come into play for some notions from synthetic biology. But returning to the expressions that we were looking at, to study other less complicated terms of the infinite volume expansion for the transfer matrix to further build up our intuition in different types of notions that we have been discussing that we can study initially from more of a general, less rigorous perspective, we can consider the following terms, some of which appear in other terms for the product representation. And this is given by the fact that instead of having all of the terms in the product representation, just start with some A coefficients, we can also have some q raised to some differential operator parameters and looking at various types of linear combinations of two parameters or two differential operators, which are then going to be preceded by some other types of similar contributions from either A coefficients, which we're not taking the dagger of, as well as the fact that this dagger, the Hermitian, the complex conjugate, can still come into play in more complicated terms of the representation, because we can have four terms which appear, or two terms which appear first, as well as having another term immediately preceding it in the superposition for the product representation, which is just a of j plus 1 of k dagger and a aj plus 2k of plus 1 of dagger. And these terms share many similarities with those appearing in the least complicated entry of the product representation from multiplying L operators, because we can see that from this term, the second term and the fourth term within this superposition, this collection of terms, which is given in the product representation, is comprised of the fact that we have some alternating signs of coefficients in which we either vary the j or the k, which can be helpful for us to have in mind, because then we can group together different terms of the superposition and how that superposition and the summation of these terms would then be resulting from an application of the bilinearity property of the Poisson bracket, and then how that pretty much unveils and immediately gives us the type of Poisson bracket that we will want to approximate for studying the Poisson structure and studying some different types of combinations of terms which appear from various interactions of in contributions of staggering and inhomogeneities in the 20 vertex model. And so the observations that we had gathered on entries of the product representation of L operators allow us to infer the form of the Poisson bracket in the asymptotic infinite volume limit. And this is given by the fact, like we had mentioned, as we always keep describing, and we've alluded to this type of set of relations at several points in the presentations in the series, is that we just have 16 of them for the two-dimensional case. And then if we're looking at the three-dimensional representation, we have 81 of them. And then the higher the number of terms which enlarge the Poisson structure and the number of Poisson brackets which appear in the Poisson structure in the three-dimensional case is coming from the fact that we have additional terms from the arbitrary representation in 2 dimensions and the arbitrary representation of the transfer matrix in 3 dimensions that we're looking to explicitly approximate and obtain the expressions for explicitly. And as we had mentioned even earlier in the presentation, the following dictionary comes into play because we're looking at different types of contributions from these sets of possible terms, and they represent, as we had reiterated several times, different types of coefficients which can appear before interactions of q raised to some differential operator, as well as q raised to subtracting two differential operators together, as well as even complex value unital mappings into an associative algebra. And the first 51 from the set of 81 relations that are parameterized on the Poisson bracket are given by this form. And sorry, I can't really zoom in, but oh, here a little bit. But anyways, you can also zoom in on YouTube too. But there are just several different types of relations which we can obtain, in which we can see that in comparison to the first set of relations from the Poisson bracket, we were having 4 terms which are appearing in the first block when we held the first entry of the 2x2 representation constant as one argument in the Poisson bracket. And then this is just showing how the additional terms appear from the set of 81 relations that we're going to ultimately we can asymptotically study from the Poisson bracket, because we're just going to have to hold one term of the 3x3 dimensional representation constant, and then we're going to have to vary over all the remaining 8 terms. So we're going to get 9 terms in total, which is then constituting the 81 possible terms, because we're having 9 entries where we're holding any one of the 9 entries of the three-dimensional representation constant, and then we're looking at varying for the other argument of the Poisson bracket, all of the other entries, including the entry that we fix from, because we're looking at the tensor product of the Poisson bracket of two transform matrices. And as we have been describing, knowing the form of the entries of the product representation allows us to have an idea of what Poisson brackets we should compute. So this is given by the fact, like we had mentioned, is that we can look at different combinatorial options and combinatorial ways in which we can have interactions from the Poisson bracket. And then this is important because because uh because it's going to demonstrate to us which terms and which entries of the Poisson brackets within this family of Poisson brackets can then be studied from different contributions, and then that pretty much immediately gives away the Poisson structure that we would like to study in three dimensions. And further remarks are in order for comparing computations with a Poisson bracket in 2 versus 3 dimensions, including the first of which states that, when we're looking at, as we had mentioned, this set of 16 relations and this set of 81 relations, it's ultimately resulting from looking at some asymptotic volume representation of either a two-dimensional representation or a three-dimensional representation. So in this way, that type of intuition from 2 dimensions, it directly carries over to 3 dimensions. But second, there's also another point that carries over, is that in 2 dimensions, we can look at subtracting these two tensor products from each other with the arbitrary representation of the transfer matrix, and that also holds for an arbitrary representation of the 3-dimensional transfer matrix. Oh yeah, and sorry, there's a typo here. The second transfer matrix that should come as an argument should be a function of u prime, not u. And then the third observation is given by the fact that we're looking at the degeneration of this tensor product of the Poisson bracket of these two-dimensional this two-dimensional representation, and how it compares with the tensor product of the Poisson bracket of these three-dimensional representations. The first of which is a function of u, and the second of which is a function of u prime. And fourth, there exists many similarities in the overall structure and the overall form of the tensor product of the Poisson bracket that we're taking in 2D and in 3D, just given by the fact that in 3D it's just an additional component because the sample space is 3 dimensions instead of 2 dimensions. And so the concluding remarks that I wanted to include so that we can close out this presentation of the series, in which we're providing more details to the viewer on the Poisson structure in 3 dimensions, is that we are adding on further detail in our discussions of Poisson structure and how patterns in terms of the product representation from taking the product of 2 L operators, and eventually one would hope an arbitrary number of L operators would arise. And we discuss how terms of the product representation determine how many terms appear in each argument of the Poisson bracket, which can be asymptotically approximated by applying the bilinearity property of the Poisson bracket when necessary. And we establish differences in 2 and 3-dimensional vertex models, in the sense that there exist boundary conditions for a 2-dimensional vertex model that have algebraic characteristics unlike other sets of 2-dimensional boundary conditions. But as we had alluded to later in the presentation in this series, we're going to discuss how for the reflecting boundary conditions, which is related to some modification of the boundary conditions that are assigned for the domain wall boundary conditions of the 2-dimensional 6-vertex model, that there can exist some type of algebraic interpretation, which is interesting to remark on and describe for maybe some source or of interest for future investigation. As given in the last bullet point, we alluded to aspects of the QISM type approach that are similar in 2 and 3 dimensions. And thanks for watching.